Okay, so pleased to introduce today's speaker, Michael Mulligan from UCR. Mike got his BS at University of Illinois Urbana-Champaign and his PhD from Stanford University, and he went on to become a postdoc at MIT and then Microsoft Research Station Q in Santa Barbara, and then Stanford University before coming here to UCR as an assistant professor. So today, Mike is going to talk to us about duality and emergent symmetry in 2D electron systems. Mike?
Okay, thanks, John. So it's a pleasure to be able to speak today. So let me share my screen. All right, so can people hear me?
Yes.
Yeah.
Okay, great. Yeah, so I want to tell you about a framework to describe quantum states of matter in two spatial dimensions. And a key component of the states that I'm going to try to describe are that they occur in the presence of strong interactions and also disorder. So before I get going, I want to thank some of my collaborators for this work, and then, of course, the various funding agencies. So the conventional theory of metals, due to Landau, is based on the idea of a free Fermi gas. So here, the idea is that the ground state of a collection of electrons corresponds to occupying the lowest energy momentum orbitals in the system. And you populate the different orbitals out to a radius called the Fermi KF, Fermi wave vector, that's determined by the number of particles in the system. And so that's the ground state. And then excited states are simply particle hole excitations where, say, an electron over here is excited out of this Fermi surface of excitations. So it turns out, and one of the triumphs of Landau Fermi liquid theory is that weak repulsive interactions essentially have no, or they don't qualitatively change this picture. So roughly similar to conventional perturbation theory, there's a one-to-one correspondence between, say, the non-interacting electron and the weakly interacting quasi-particle excitation. So one of the successes of this theory is in terms of thinking about this as a parent state of low temperature states of matter. So in particular, in two spatial dimensions, there's two possibilities for where this Fermi liquid can go. So if perchance there's an effective attractive interaction between the electrons, perhaps mediated by vibrations of the solid, then at sufficiently low temperatures, the electronic system can transition into a new state of matter, in particular the superconductor, characterized by vanishing resistance. On the other hand, suppose there's no traction and there's randomness or disorder in the system, more about that later, then the system is forced into an insulating state where the resistance diverges at zero temperature. So these are the two options given to the Fermi liquid theory. And as you can tell, both of these options are, at least in part, characterized by transport properties of the system. Okay, so you apply a voltage and measure the resulting current along that voltage, and whether whether you get a large voltage or a small voltage tells you which state you're in. So much for the possibilities of the Fermi liquid when there's no transverse magnetic field applied. If there is a transverse magnetic field, the structure of the single particle states is dramatically modified. So we lose this kind of momentum space picture where you fill up a Fermi sea, and instead you have to go to a real space picture where these electrons are moving in some sort of circles and orbits. And here, what I've tried to illustrate is a picture of the set of states that the electron has available to it. So it fills up so-called Landau orbitals, and eventually you just keep on filling up the plane with these circles. So this filling of Landau levels is precisely what the integer quantum Hall effect is. So this is the really the third electronic option for a low temperature state of these collection of electrons. So this, how many Landau levels you fill is characterized by this number called nu, which is called the electrical filling fraction, and roughly speaking, it's just the electron density over the applied magnetic field. All right, so the idea here's an energy picture diagram, bottom left panel, and so as I populate more and more of these Landau levels, I go from, say, integer quantum Hall state characterized by these different plateaus. So I transition between these different plateaus in the Hall conductivity. One thing you'll notice is that this state of matter, this integer quantum Hall state of matter, now we can't just use the one resistivity or conductivity along the direction of the applied voltage. In addition, we need to think about, if we drive a current down this so-called Hall bar, then we've got to measure both the voltage drop along the Hall bar and likewise transverse to this Hall bar. So one is name is longitudinal conductivity or resistivity, and the Hall or transverse conductivity. And so the signature of the quantum Hall effect is these steps in the Hall conductivity or resistivity. Coincident with these steps is a vanishing of the longitudinal resistance. This should be contrasted with the classical or high temperature picture for such states, where you just get a straight line for the resistance and the Hall resistance. All right, any questions about this so far? So, I mean, this is a pretty remarkable achievement of the Landau Fermi liquid theory in terms of giving us a framework to understand these different quantum or low temperature states of matter. However, there's more. So the need to go beyond Fermi liquid theory is captured by this haiku. So it says, instability of a tranquil Fermi sea, broken symmetry. This is a physics talk, so let me give you a translation. So the translation is, a relevant perturbation drives the Landau Fermi liquid into a superconducting state. And so what this essentially says is, you can only do so much with the Fermi liquid theory. And if you want to find other states of matter or understand other states of matter, you're going to have to do something else. You're going to have to develop a new theory. So this need to develop a new theory is beautifully illustrated in these famous by the famous high temperature superconductors. So on the left panel here, I've got a schematic phase diagram of these materials of how they behave as a function of temperature and particle density. And there's kind of, if you know, in quotes, conventional phases of an antiferromagnetic state having to do with the spins of the electrons. There's a superconducting state. And the novelty, or one of the novelties at least, here is that the temperature at which you enter the superconducting state is orders of magnitude larger than in a conventional superconductor obtained from Fermi liquid theory. And another interesting feature is that the resistivity, in particular the longitudinal resistivity, varies linearly with the temperature of the system. And this is, this should be contrasted with conventional Fermi liquid behavior, in which the temperature exponent here of the resistivity is 2 or greater. And remarkably, this linear resistivity persists for orders of magnitude of temperature. Okay. So there's been a lot of work devoted to trying to understand this and other behaviors in this phase diagram. So there's something called the pseudogap. And the idea is that some sort of non-Fermi liquid is at the heart of this linear resistance, and that non-Fermi liquid acts as a parent state for the unconventional elevated transition temperature superconductivity. So one hypothesis is that this strange metal, this thing that exhibits weird resistance as a function of temperature, is due to an underlying phase transition in the system. And the effects of such phase transitions are, or more precisely, fluctuations of a order parameter characterizing that transition as it interacts with the electrons in the system, is illustrated nicely in some of these classic experiments on thin superconducting films. So in these experiments, naturally the system in this two-dimensional system wants to be a superconductor. However, when you apply a magnetic field, the system transitions into a different phase, an insulating phase. In the vicinity of this transition, if you look carefully at the low temperature resistance, what you find, so low temperature in this figure is to the right, you find some sort of saturation of the resistance. It turns out we have yet to have a satisfactory theory for any of this. Okay. The theory that describes this is yet to be discovered. So my focus today is on a related system, the so-called half-filled lowest Landau level. So this is a collection of electrons at filling fraction 1/2, so a bunch of electrons in 2 dimensions in the presence of a strong magnetic field. And the basic phase diagram, again, is illustrated here. And in addition to those phases, those quantum Hall phases, characterized by integers, we now get a bunch of fractions. Okay, so these so-called fractional quantum Hall states go beyond Landau theory and really calls for a new framework. Now it may seem kind of overwhelming, how we're going to deal with really this infinite or infinite collection of different quantum states corresponding to these different plateaus. But what I want to try to argue for you today is that a lot of the phenomenology can be understood from thinking about this state living at half-filling fraction. And my hope is that at least some of this theoretical technology that I'm going to describe will be useful for some of the other systems I talked about. So these thin films, or even perhaps these cuprate superconductors. All right, are there any questions? All right, so here's the outline of my talk. So I first want to give you a physical picture for this theory of the half-filled Landau level. This has to do with so-called composite fermions, which are shown here in this lab picture. And then I want to talk about some evidence for this physical picture and some challenges. Once I'm done with that, I'll tell you how you can use this theory for the half-filled Landau level in a sense as a seed or generator for understanding the other states in this quantum Hall phase diagram. Then I'll conclude with a selection of some open problems. All right, any questions before I get going? Okay, so it's worthwhile to perhaps step back for a second, if you're not, and think, why three dimensions or why 2 dimensions? So, the basic statement is, physics is dimension dependent. So, in particular, there are no stable planetary orbits in spatial dimensions greater than 3. So, if you like anthropic reasoning, this gives you reasoning for why we live in 3 spatial dimensions. So here today, what I'm interested in is not 3 spatial dimensions, but 3 space-time dimensions. And the basic feature in here has to do with statistics of identical particles. So in quantum mechanics, we're taught that if we have a collection of identical particles, they come in 2 flavors. They can either be bosons or fermions. Now, it turns out that in 2 spatial dimensions, that the particles can have any statistics. This, ultimately is due to representations of the so-called Braid group, but such particles for which the statistics can be anything are called anyons. So let me give you, a constructive way to understand such particles. So the physical picture is, let's consider a solenoid, a flux tube, which carries some magnetic flux phi, and I'll have it be pointing downward. And we'll imagine some charged particle, Q, that's orbiting this solenoid. So as we learned from Aharonov and Bohm, even if the magnetic field is entirely contained in this flux tube, the vector potential giving rise to that magnetic field still has an influence on the quantum particle. So in particular, the wave function of the particle as it orbits the flux tube, it picks up a phase gamma here, which depends on the amount of flux you've got going through that tube, capital phi. Now let's imagine that we've got 2 such charge flux composites, in particular they're identical charge flux composites. And what we want to imagine doing is exchanging them, okay? So we take this guy over to the left and then the guy on the left over to the right. So the 2 particle, or sorry, the 2 composite particle wave function, it likewise obtains a phase upon this exchange. And there's 2 contributions to this phase. The first is essentially due to this Aharonov-Bohm phase, as this first particle on the right moves halfway around the flux tube on the left. That happens for both the particle on the right and the particle on the left, and they contribute, a total phase similar to before. And in addition, there's a contribution that's depending on the statistics of this particle Q, which I'm calling the spin of particle Q. So an anion now is simply is simply a reflection of the fact that this flux phi going through this tube can in principle be anything you want. So when this ratio Q capital phi over the flux quantum phi naught is between 0.5, the statistics of one of these charged flux composites is neither boson or fermion, but something in between. A nice example of how this can occur in a sort of conventional system is if we take a superconductor, conventional superconductor, and we imagine the charged Q particle is an electron. Here we have in this case the flux tubes are H over 2e vortices. If we consider their composite, the resulting composite particle is a boson. Questions? So I want to do something similar here. So I want to consider, another electron, and if I attach, or if I form the composite with two vortices, what I'll do is change it not into the collective state won't be a boson, but instead it's going to be some sort of new fermion. I'm going to call that new fermion a composite fermion. When I'm rearranging this equation, we see that a composite fermion here attached to two vortices pointing downward is the same as an electron. So somehow this is a way to describe electrons in terms of this composite fermion vortex composite. So that's the sort of composite particle that I'm going to focus on today. And to simplify the notation, so I don't draw this all the time, I'm gonna instead indicate this composite by this red disk and the two blue arrows going down. So the point of this, the utility of this, for at least for these electrons in a strong magnetic field, comes when we consider a collection of such composites, of composite fermion and fluxes. So let's consider a collection characterized by some density rho, which is equal to the electron density, and let's put them in the presence of some external magnetic field transverse, right? Well, the total field is just the external field minus the magnetic flux contributed by these vortex tubes, flux tubes. And so the total field, or effective field, seen by the composite fermions is reduced in this manner. And in particular, when the external field is tuned in a precise way to the composite fermion density or electron density, the effective field can vanish. This occurs precisely at 1/2 filling fraction. So somehow, the physics of electrons in this, incredibly strong 25 Tesla magnetic field, we can trade it for that of free composite fermions in zero magnetic field. Any question on that idea? All right, so this is progress. And then furthermore, this collection, if I just focus inside this red box, these collection of fractional quantum Hall states indexed by these fractions can likewise be understood from this simple-minded framework. So if I just consider electrons at 1/3 filling fraction, that's living, unfortunately not in this figure, but just to the right here, then what we've got is a so-called partially filled Landau level. The point is that this fraction here is not an integer. Well, that's a hard problem. It's hard because the state that the electrons choose is very sensitive to the interactions, and understanding the effect is challenging. However, if we instead make use of this composite fermion framework, it turns out that the 1/3 filling fraction of electrons is equal to an integer filling of composite fermions. And so we just do what we should, and that is to fill up the lambda level of composite fermions. More generally, a selection, a Jane series of so-called Jane series of fraction quantum Hall states can be easily understood in this simple-minded picture. So a useful test of this hypothesis that composite fermions behave similarly to a Fermi liquid and zero field involves what are called quantum oscillations. So these refer to little wiggles in measurable quantities as a function of an applied magnetic field. So here, what I'm showing you are these wiggles or oscillations in the resistivity. So there's one characteristic sort of oscillation known as Shubnikov-de Haas oscillations, and what they do is they occur, some large distance, if you like, away from the zero field state. Now, in this quantum Hall state, if we go too far away from half filling, we're going to enter some quantum Hall state, and so these oscillations are going to be obstructed. We're not going to be able to see them. So a refinement of this idea involves patterning a periodic potential on this 2D electron gas. In this case, what this does is introduces an additional length scale A here, characterizing that potential, and it allows oscillations much closer to the state of interest. So in particular, if we're looking in this right panel here, it allows us to measure possible oscillations and then infer the Fermi wave vector of these emergent composite fermion particles. So the consistency of this picture, namely that composite fermions, or rather that there's a composite Fermi liquid that emerges at half filling fraction, it has been confirmed by these quantum oscillation experiments. All right, so the summary of this so far is that there's an emergent composite Fermi C at half filling fraction. Questions on that? Now, okay, you say, okay, that's great, but there are some fundamental questions that this picture presents. So they come in kind of two flavors. So kinematic, or things having to do with the symmetry of the state, and dynamics. So kinematics are, how do you preserve this symmetry called particle symmetry? Dynamics has to do with, well, if you've got a bunch of free composite fermions, well, there's inevitably some impurities in your system. And Anderson taught us that such systems become an insulator at zero temperature. So, in what sense does this Fermi C survive to the lowest temperatures? So let me clarify these two objections. So disorder. So what disorder? What's disorder? Well, at a fundamental level, they represent violations of translational or rotational symmetry in your system, and they're inevitably present in any real material. And the way we can think about it is including in our electron Hamiltonian some function v of x, some random function. So that sounds pretty daunting. So what that means is you compute quantities for an unknown function v of x, and then averages the result as over a distribution of possible VFXs. So the picture of randomness in electron systems is that when the disorder is, quote, weak, then the role of disorder is to impart a finite conductivity of the system. So the conductivity is finite, and the order of magnitude of that has to do with the scattering time of these particles as they scatter from one impurity to another. On the other hand, if the disorder is strong, then there's a you can think about a 1D particle in an attracted delta function potential that localizes the wave function, and so the wave function of a particle becomes exponentially localized with some localization length c. And the conclusion, at least in 2 spatial dimensions, is that all free electron states in the presence of disorder become insulators at 0 temperature. So the question that I want to ask is, what about free composite fermions? So that's a clarification of point number 1. The second point has to do with symmetries of the system. So the energy spectrum of electrons in a magnetic field is characterized by this cyclotron energy just going as the magnetic field over the effective mass of the particles. And so this symmetry, particle symmetry, obtains in this idealized limit where this energy difference goes to infinity. And the basic premise is that in this hypothetical limit, the electron Hamiltonian essentially has 2 choices for how do you want to describe the physics. You can either describe the physics as populating, and let's focus on the lowest Landau level state. So nu here is between 0 and 1. You can either think of the physics at some filling fraction nu as filling an empty vacuum with electrons, or alternatively as depleting filled Landau level with holes. And this particle symmetry transformation, it relates states at filling fraction nu and 1 minus nu. So in particular, a state at 1/3 is the same as holes at 1/3 or electrons at 2/3. Now, the important point and subtle point is that this isn't a symmetry of the system. Okay, it's not a microscopic symmetry. This ratio here is not infinite. Nevertheless, it appears to be an emergent symmetry of the system. So in particular, if we just focus on the panels on the right here, the top one is the longitudinal conductivity, the bottom one is the Hall conductivity. What they're essentially saying, it's enough to look at the top one here, is that you measure the longitudinal conductivity as you sweep over the filling fraction, and then you flip the figure. So the black is just a conventional measurement, and then the red is when you flip it about nu equal to 1/2. And to good approximation, these red and black curves line right up onto one another. So this particle symmetry is this reflection symmetry of this transport. This symmetry also appears to be observed by, if you look at the energies of excitations in nearby fractional quantum Hall states. So I talked about nu equal 1/3 being related to nu equal 2/3. The excitations there appear to high accuracy to be the same for these particle hole related states. Now, an important consequence that I'll focus on here is that precisely at half filling fraction, the composite fermions are constrained to exhibit a particular Hall conductivity. So they have to be minus 1/2 E squared over H. Now, that seems okay until you realize how is this possible when these particles, these composite particles, see zero effective field? Said differently, a Hall conductivity is the result of time reversal symmetry breaking. And if these particles don't see any magnetic field, how are they going to get this order 1 Hall conductivity? So I'm going to argue that these two objections, namely about symmetry and dynamics, have a common explanation or resolution. Before I do that, are there other questions about the idea? So the key thing to think about, it seems, is the way these composite particles couple to impurities or randomness. So not only do they care about this randomness in the scale of potential, but in addition, there's an additional form of randomness that's generated. This randomness is generated in part because of these fluxes that these particles are attached to. Right. So in addition to the scale of potential randomness that the particles see, they additionally see a random magnetic field. So the basic picture is that you've got some scale of potential randomness, this red curve here, and in a precisely correlated way, there's vector potential randomness that accompanies it. Now this is kind of sounds crazy. No one in their right mind would ever consider this sort of random problem, but it appears quite naturally in this composite fermion framework. So let's see the effects of this sort of coupling. So the first thing to try to think about is how do you evade that time reversal breaking constraint? And so let's consider a classical picture where we have two puddles of that correspond to the deviations of from some of the density of the particles from some homogeneous, and calculate the average filling fraction in the system. So we just add up the deviation from the blue puddle and add up the deviation from the red puddle, and in the presence of this highly unconventional randomness between the vector and scalar potentials, there's a coherent contribution to the Hall conductivity. Now, this is a classical picture, which happens to give dead on the apparently right answer, but it can be confirmed in fact by numerical calculations. Now, what's the significance of this result, this Hall conductivity, which is equal to 1/2 E squared over H? So we can understand this by thinking about Laughlin's argument for the integer quantum Hall effect. So the basic statement is, if you have a bunch of particles in which there are no interactions and the conductivity vanishes, then such particles have to exhibit a Hall conductivity, which is some integer, capital N, times E squared over H. The basic picture for this has to do with driving a current around some hypothetical ribbon or a cylinder in response to some changing flux. And in response to that flux, there's a Hall voltage which develops. Now, there's two ways to violate the assumptions of Laughlin's argument. We can either add interactions or add some conductivity to the system. So the first option at vanishing conductivity is found actually in so-called higher Landau levels at this 5/2 state. On the other hand, without interactions and this half Hall conductivity, the contrapositive to Laughlin's argument implies that these free composite fermions cannot be localized. They cannot form an insulator. Rather, they form some sort of non-Fermi liquid metallic state. All right, so the summary, the physical picture here is that strongly interacting electrons in a transverse magnetic field have an alternative description in terms of this composite Fermi liquid. And this composite Fermi liquid is apparently a non-Fermi liquid state of matter, and we can understand it as a parent state for these fractional quantum Hall states, which go beyond Landau theory. Okay, are there any questions about this idea? Okay, so much for the half-filled state. Now let's try to tackle some of these other states here. So these anomalous metals are occurring in a filling fraction 1/4 or filling fraction 3/4. So it's not obvious, how we should think about these states, or if they're related, if at all, to the half-filled state. So a key insight actually comes from an experimental puzzle and thinking about a closely related set of states. So in the left panel here, we've again got some transport measurements. This is just the longitudinal conductivity or resistivity rho XX. And what's happening here is as one varies the magnetic field, one is transitioning from, say, an integer Hall state to another integer Hall state. So nu equal to 1, nu equal to 2. The right panel, same thing, but this time for fractional quantum Hall states. So here we're transiting from the 1/3 state to a 2/5 state. All right, so it seems very different. Now, what one can do is we can for this phase transition between these two states, we can infer a sort of universal exponent, some sort of correlation length, by measuring how the width of this little peak thingy depends on temperature. So this defines a correlation length critical exponent, which is supposed to characterize the theory for this phase transition. Now, a remarkable thing is that these distinct phase transitions appear to have the same critical exponents. This behavior is sometimes called super universality. So the theoretical idea in linking these all these collections of states in this quantum Hall phase diagram comes from thinking about the conductivity which characterizes the different fractional quantum Hall states. So there's two independent components of the conductivity tensor, sigma xx and sigma xy, that we can use, excuse me, to form a complex number. And the different states, different fractional quantum Hall states, can be mapped or transformed, or at least their conductivity can be transformed to each other by so-called modular transformations. Okay, in the theory of complex analysis, you've got some number which is on the upper half plane, and you can map that to itself under modular transformations. All right. Now, the remarkable thing is, discovered by Kivelson and Witten, is that these transformations which act on an observable of your theory, the transport, the conductivity, can actually be used to map different theories to one another. So the theory of these composite fermions at half filling fraction can be mapped to a theory of particles at quarter filling. What's more is that that within the two different a priori different theories, one can argue that this correlation length exponent is the same between different theories. Now I should say that these calculations were done on a bit more symmetric models than is appropriate for the systems of interest, but nevertheless, this general behavior is rather remarkable, namely that different phase transitions can have the same critical exponents. Okay, so that's what I had to say in terms of describing composite particle description of the half-filled Landau level and how that theory can be used to describe other quantum states in this phase diagram. Any question before I end with a collection of open problems? Okay, so I've got a few different questions. So the first has to do with an analytic description of when these composite particles are exhibiting a Hall conductivity, a conductivity, longitudinal conductivity of order 1. So in physics, it's easy, well, in some sense, to get 0 and infinity, but getting a finite number is generally pretty hard. And the kind of way to understand the nature of this problem is it's somewhat analogous to thinking about having a Fermi liquid theory, which wants to become a superconductor, but you don't know the Landau-Ginzburg theory of superconductivity. Okay, so we somehow need to develop that theory. So far, what we've got is what's called a nonlinear sigma model, which describes the charge fluctuations in the system, and it's well defined only or well controlled rather when this longitudinal conductivity is very large compared to the quantum of conductance, and so it's completely open trying to develop a theory which is applicable in this regime of interest to the actual experiments. Now, what I've been telling you about, more or less the whole talk, is I've been discussing free composite fermions. That is, composite fermions without any interactions. Well, it turns out that this limit where the composite fermions are not interacting, they're just a free gas of composite fermions, is appropriate to a limit where the Coulomb interaction is infinite. Now, this fact that the Coulomb interaction is infinite, but gives you free particles, is a little bit like conventional electromagnetic duality, where Maxwell's equations are invariant under the exchange of the electric and magnetic field, so long as you invert the coupling. And so the question is, how do you move away from this infinite Coulomb coupling limit? Well, the theory tells us that if we want to do that, all right, no problem doing that. However, the cost is that we've got to introduce fluctuations of this this field, which is tying composite fermions to flux. Okay, this is this little a vector potential field. Now that's a challenging problem, and thus far what we've done is tackled a related problem, which has to do with composite fermions not at finite density, which appropriate to these systems that I've been talking to you about, but rather appropriate to composite fermions at zero density. In particular, you can think about graphene at the Dirac point. And what we've been able to find is rather non-trivial low temperature states. So as the temperature, these arrows correspond to as you lower the temperature, a non-trivial metallic state is found, which is stabilized by the presence of both, this disorder and a interaction. And so an obvious question is, how do I turn on a finite density of states in this system? Now, I talked about the measurement, excuse me, of the Fermi surface of these composite particles using quantum oscillation. These it wiggles in the longitudinal resistivity. And if you happen to stare at that experimental plot, you'd notice that there's a disagreement between the conventional theory and an experiment. It's about a 2% disagreement. So here in this plot, which I'm reproducing it, the conventional theory are these blue wiggles, and the experiments are these black hash marks. And so there's a 2% disagreement kind of far away from half filling, which gets reduced as you go closer and closer to the metallic state. And what with Marta Mitra, what we were able to show is at least one interpretation of this disagreement is that these gauge fluctuations, which were turned off, need to be turned on, and that is, this disagreement is a reflection of some emergent gauge forces in the system. Now, whether this, the exact comparison to experiment is important, and perhaps incorporating other symmetries might further improve this relation between the theoretical prediction and the experiment. Two other questions which are we're thinking about here have to do with, why is a composite Fermi liquid good? Well, it gives you a simple way to understand some infinite collection, really, of fraction quantum Hall states. But there's more, okay? In addition, there's a sort of superconducting instability discussed by Reed and Green of composite particles, and they can exhibit so-called non-abelian fractional quantum Hall state, where the particles in that state have not just, when you exchange them, you don't just get a phase, but in fact, the space of states of a collection of particles is has dimension greater than 1, and exchanging those particles, you get a matrix that acts on the state, right? So such a state is thought to exist at 5 filling fraction, and the question is, how can we, can we better understand, how the composite Fermi liquid transitions to such a state, or possibly others? There's not just so-called Pfaffian state, but a number of different other states, and then in particular, what are their transport characteristics? Now, for the entire talk until now, I've been talking about local probes of condensed matter systems, namely probing the system in terms of a local observable, like the charge. Now, in recent years, it's been appreciated that non-local observables can give you some very insightful information about a quantum state. So a famous example is the entanglement entropy, which works as follows. So if we have a state, so we partition a state in terms of a disk and everything outside of it, and we compute the von Neumann entropy, the reduced density matrix of the degrees of freedom living in that disk. Well, the entanglement entropy, S sub A, takes a characteristic form, and this coefficient that's independent of the size of our disk has some sort of universal information about that quantum state. And so if we're talking about fractional quantum Hall states, that gamma constant is related to the sort of quasi-particles which can exist in your system. If we're talking about gapless states, this subleading constant actually generalizes, at least for relativistic theories, the central charge, and in fact, it can constrain, which states can be related to each other by perturbation. With Pak and Hamed and Jeffrey, we investigated how related measures of entanglement can characterize higher forms of entanglement in your quantum state. So, the Bell state can characterize your bipartite entanglement, but it's in some sense insensitive to higher point entanglement. And so what we found is that multi-part entanglement, that is entanglement of 3 or more parties, is highly sensitive in fractional quantum Hall states to the topological properties of that state. Now, it's a very open question, what are the other forms of entanglement? And furthermore, to what extent can any of these ideas be applied to states that occur at a phase transition? So with that, thank you.
Thanks, Mike. Questions? Anyone have a question? I don't hear any questions. So thanks again, Mike, for your talk.
Sure.
Okay, thanks everyone.
Yep.
Bye-bye.
Thank you.
Hey, Mike, can I